All right, welcome to Physics Video 1.4. We're going to learn about position time graphs today. So by the end of this video, you should be able to do a few things. If I give you a position time graph, you should be able to explain the motion that created that graph. And then similarly, if I give you a graph, you should be able to do a few simple calculations, like you should be able to find the average velocity, the displacement, and the time for different portions of that graph. And then finally, if I give you a scenario in which an object is moving around, you should be able to draw the graph that describes the motion in that scenario. Okay? So before we do anything, we really need to make sure you guys have a good understanding of what position is. So remember, position describes the location of an object on a number line. Okay? So for example, if Roy is at his house, then we're going to say that Roy's position is 0 miles. If Roy is over here at the Quickie Mart, then we're going to say that his position is 15 miles. Okay? So it's just where you're at on a number line. Okay? The problem is that objects move. So like in this example, it's not possible for Roy to be at both of these positions at the same time. So time is also important. In other words, if Roy walks from his house to the Quickie Mart, then he's got a whole bunch of different positions, right? As he moves, his position hits every number between 0 and 15. So, if I want to represent motion, suppose I gave you a problem and I said, Roy walks from his house to the Quickie Mart in 3 hours or whatever. Then you could say, oh, cool, well, let's see, he started here, so I'm going to draw this. And then let's see, he walks over here to the Quickie Mart. So now he's there. And so the drawing sort of illustrates, that he walked from his house to Quickie Mart. But the problem is the drawing doesn't tell us anything about how long it took. Okay? So if I wanted to, I could say, oh, well, that took him 3 hours. Awesome. But the problem is that it doesn't tell us, for example, maybe we wanted to know at what time he got to White Castle, or maybe we wanted to know at what time he got to Sally's house, or whatever. This doesn't tell us that. All right? So what we're going to do is we're going to make what's called a position time graph. All right? So the position time graph looks like this. There's going to be two axes. The horizontal axis is always time, measured in whatever units, in this case, hours. And then the vertical axis is position. So this is a little bit weird because my number line runs horizontally, but it always goes on the vertical axis on our graph here. Okay? So our position is measured in miles. So what I would need to do then is if I wanted to represent this, if I wanted to represent Roy walking from his house to the Quickie Mart in 3 hours, then I'd need to put 3 hours on my time axis. So 1, 2, 3. And then I'd need to draw in my positions, 0. So you'd go 1, 2, 3, 4, all the way up to 15. Okay, and so then I can plot my 2 points. At time 0, when we first saw Roy, his position was 0. After 3 hours, his position was 15. And so there's my graph. All right, and so then the idea is, if your graph is drawn carefully, which mine is not, you can figure out, at what times he got to different points. So like if I wanted to know what time he got to White Castle, then I'd go, all right, well, that's a position of 3, right? So I'd go up to a position of 3, 1, 2, 3, read the graph, and figure out what the time was there. Okay? So this graph is done very sloppily. So let's kind of clean this up a little bit and make kind of a nicer graph. Okay? So take a minute and actually draw this graph out. Okay? You don't need to use a ruler, but try your best to draw your graph so that your time goes from 0 all the way up to 10, and your position should go from 0 up to 20. Okay? So pause the video, do that now. Okay, cool. So now that you've done that, let's make some different graphs. All right? I'm going to color code mine. I'm going to use the usual red, blue, and green, and maybe black. So here we go. So let's do this. Let's suppose on day 1, Roy leaves his house, and he walks at a velocity of, let's say, 2 miles per hour. He's just out for a stroll. Okay? So what that means is every hour he's going to go 2 miles, right? So he's going to start here at time 0. His position is going to be 0. All right? After 1 hour, he'll have gone 2 miles. After 2 hours, he'll have gone 4, 6, 8, 10, etc. So I'm going to plot that on my graph down here. Okay? So after 1 hour, he'll have gone 2 miles. After 2 hours, he'll have gone 4. 3 gets us 6. 4 gets us 8, right? He's just going 2 miles every hour. So 2 miles, 2 more 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 miles, right? So we can connect the dots. I'm going to just sort of freehand this in. Ideally, I would use a ruler, but I'm not not going to do that. So there we go. So there's our line. All right, so what that line represents is Roy moving at a velocity of 2 miles per hour. All right. Now, let's suppose the next day he goes for a walk, but maybe the next day he only goes 1 mile per hour. Okay, so that means that instead of him going 2 miles every hour, he's only going to go 1 mile every hour. So now my graph is going to look like this. Right, and then connect the dots. You get a graph that looks like that. So there my velocity is 1 mile per hour. All right, and then maybe the next day he is in a big hurry. So maybe the next day he goes at, I don't know, 5 miles per hour. So that means every hour he's going to go 5 miles. So he's going to start out here. After 1 hour he'll be at 5, 10, 15, 20. So after 1 hour he'll be at 5. After 2 hours, 10. 3 hours, 15. 4 hours, 20. Okay. So what do you notice? Well, let's see. The green line down here at the bottom is 1 mile an hour. This is 2 miles an hour. And this is 5 miles an hour. It seems like the steeper the graph is, the faster the object is moving, right? Okay, so that is one of the things that we're going to learn. All right, so what have we learned? Thing number 1. The steeper your position time graph is, position time graph is, the faster the object is moving. So a lot of times physics teachers will tell students that the slope of the line is the velocity, right? Slope is a measure of how steep the line is, and velocity is a measure of how fast the line is. So that's basically what's going on here. So the big difference, though, is that velocity also includes direction. All right, and we haven't talked at all about direction here. We've talked about steepness, right? The steeper it is, the faster it is, but we haven't talked about direction. Okay, so let's go back now and talk about direction. Okay, so in all of these problems that we've done so far, our object was moving this way on our number line, right? Okay, so what happens if Roy, starts maybe at the Quickie Mart, but then walks back to his house? All right, so let's kind of clean up the graph here. I'm just going to clean up the number line, actually. We'll keep dirtying up our graph. All right, so let's suppose that Roy starts at the Quickie Mart and then walks this way at, I don't know, maybe 3 miles per hour. All right, so now our velocity is going to be 3 miles per hour, but because he's going backwards, we have to make it negative, right? Okay, so here's what's going to happen. He's going to start at a position of 15, and then every hour he's going to go back 3, right? So 1, 2, 3. 1, 2, 3. So he's going to be at 12, then at 9, then at 6, etc. So after 1 hour, he's at 12, 9, 6, 3, 0. So now for that black one that I just drew, my velocity is negative 3 miles per hour. Okay, so we've learned something else big here, which is this, that if you're going backwards or in some sort of negative direction, that your line will slope downhill. All right, so let's write that down. 2. If the object is moving in a negative direction, the position time graph slopes downhill. Like that. Okay? All right, so the last thing that we need to talk about is this. In all of the graphs that we've done so far, our object has been moving at a constant velocity, right? Like in this last example, every hour he went 3 miles, every hour 3 miles, etc., right? But in the real world, that doesn't happen, right? In the real world, objects speed up, they slow down, right? And so that changes the way that the graph looks. Okay, so let's think about this. Let's suppose that we had one last object that started out moving very slowly, and then it gradually sped up and went faster and faster and faster and faster. Okay, so let's think about what's going to happen. What color do I want to use? I think I'm going to use black again. All right, so we'll go back to Roy's house. We're going to move forward again. We're going to start at Roy's house, though. All right, so let's suppose he starts out moving slowly. All right, so maybe in the first hour, he only goes 1 mile. Okay, so, all right, but then he speeds up. So in the next hour, maybe he goes 2 miles. And then in the next hour, maybe he goes 3 miles, because now he's going even faster. In the next hour, maybe he goes 4 miles. And then 5 miles, 1, 2, 3, 4, 5. Okay, what is the graph doing? It's no longer a straight line, is it? It curves, right? So, the third thing that we're going to learn then is this. If the position time graph is a straight line, and by straight I don't mean horizontally, guys, I mean not curved. In fact, let's write that. If the position time graph is not curved, the velocity is constant. If it is curved, the velocities change it. And notice in that last example, the line started out not very steep, and then it got steeper, right? So that meant that the object was speeding up, right? Because steeper is faster. Okay? So that is target 1.4.1. So first of all, up at the top of the screen up here, you can see there's this little, above that green line I just drew, you've got this dude standing here, this James Bond looking dude, standing on a ruler, right? So that ruler represents his position. It's telling you where he's at different times. All right, so what I'm going to do is I'm going to go over here, and I'm going to type in a different position. Let's have him start at a position of -9. So notice he moved to a position of -9, right? All right, so here's what we learned. We learned that the faster you're going, the steeper the graph is. All right, so let's have him move forward slowly. I'm going to have him move at 1 meter per second. And what I want you to do is I want you to watch the position time graph. This bottom one down here is our velocity time graph. We'll learn about that more later on, okay? So here we go, boom. So there's our position time graph. Notice he's moving 1 meter every second. So right now he's here, 1, 2, 3, 4, 5, etc. Every second he moves 1 meter, right? Until he runs into the wall. That was really loud. Let me turn off the sound so that doesn't happen again. So he ran into the wall, right? So that line right there was 1 meter per second. Okay? So what we learned was the faster he's going, the steeper the graph is, right? So let's go back and let's do it again. This time let's make the velocity a bigger number. How about, I don't know, 4 meters a second. So we'll jump him back to his same starting spot. This time we'll make the velocity 4 meters per second. All right, and watch what happens. Oh, the graph is way steeper, right? Because every second he moves a bigger distance, right? Okay, so that's that. Now, if I want him to turn around and come backwards, then what's going to happen is the line will slope downhill. So I don't know if you can see the graph right now. We're at 9 seconds. And the graph is way up here. His position's 10, right? So I'm not going to clear it. I'm just going to have him turn around and go backwards. All right, so my graph is going to resume right here where my little arrow is. All right, let's make his velocity negative something. So let's have him walk back at, I don't know, about 3 meters a second. So notice I typed in a negative velocity here to have him move in a negative direction. And he even turned around and faced in a negative direction, right? Okay, and let's hit play. So now the graph slopes downhill, right? Okay, so that is that. All right, and then the last thing I need to show you is what happens if he starts out slowly and then speeds up, okay? So let me see if I can do this. It's totally not going to work. All right, so I got to open up another graph for this. So we want him to speed up. We're going to learn about acceleration soon here. I'm going to have him accelerate. All right, and watch what the graph does here. Let me get rid of this. Delete. All right, so here we go. We're going to start out slow and then speed up. So watch what happens. See, he's moving pretty slow right now, but now he's going faster and faster and faster. And as he speeds up, the graph gets steeper and steeper until he runs into the wall. All right, there we go. The next thing you need to be able to do is this. If I give you a position time graph like this one here, you need to be able to do some calculations, okay? So for a moment, let's focus on this portion of the position time graph, okay? So what this is telling me is that my object, whatever this object is, it's moving from a position of -12 to a position of 24, to a position of 24 in the time that it took to go from 2 seconds to 5 seconds. Okay? So let's talk first of all about the time. So finding the time that elapses during a given interval, you literally just subtract the 2 times. So for this red chunk that I drew here, we're going from 2 to 5 seconds. That's 3 seconds, right? 5 minus 2. Okay? So time equals 3 seconds for that chunk. Now, the displacement, you guys know how to do this. There's a couple of ways of doing it. You can do it either just kind of conceptually by thinking about what you know about position, or you can use an equation. What I tend to find is that most people like to use an equation. So if you're using a position time graph, the easiest way to find displacement is to take your final position and subtract your initial position. Okay? So for us, let's see, our final position, final means at the end, right? So that's going to be at the end of the time. So our final position is 24, right? Oops. Why won't my smartboard work? 24 meters, right? And then my starting position is -12 meters, right? So to find my displacement, I'm going to take my final minus my initial, and I'm going to get 36 meters. All right? If you'd prefer, you can think about it this way. You're walking from a position of -12 to a position of 24, right? You're starting here and then walking all the way over to here. So to do that, you got to go 12 miles to get to 0, or meters, sorry. Another 24. 12 and 24 is a total of 36 meters, right? My smiley face is a cyclops. There we go. All right, so that's all that's going on there. That's our displacement. We're walking from -12 all the way up to 24, so our displacement is going to be 36 meters. Okay? So that's that. And then finally, to find the average velocity, well, that's like the first equation we learned in this trimester, right? Or this class, since we're not going to be on trimesters forever here. So our average velocity is 36 meters divided by 3 seconds. So that means you're going 12 meters per second. Okay, so that is it. I'm going to stop here and make a separate video out of the last learning target. So that right there was learning target 1.4.2, how to do the calculations on the graph. All right, and then I'll do video 1.4b that tells you how to do the how to draw the graph. Cool.